Okay, so welcome back to the third part of von Neumann analysis of the initial value problem discretization using backward in time and forward in space. So this was the equation we ended up getting last time, where n is the index for time and I is the index for the space. So we did the backward in time and forward in the space. Our goal is to show that this is always a stable. So we're going to do von Neumann analysis later on, and show that the magnification or the amplitude of the perturbation doesn't change in time. Before actually going to the details of von Neumann analysis, we want to see how we can solve this problem. So we know that every variable at the higher index in time would be unknown, and everything at the lower index in time would be the known values. All right, so then in this equation, every variable at time n is going to be unknown. So I have the ui n and ui minus 1 and n on the left side, and then the n minus 1 variables on the right side, which is known. Okay, so I have two unknowns with one equation. I cannot solve this. I have to have other equations written and include those into the system. So it looks like we're going to solve a system of equations to solve for, or to find the du and I. Okay, so if we put I equal 2, then the first equation we get is minus alpha times u1, so minus alpha times u1 at time n, and then plus 1 plus alpha times ui, which is 2, so it's going to be u2 at time n, and that's what I have the first line of my equation here. If you multiply this row by that vector, you get minus alpha times u1 at time n plus 1 plus alpha times u2 at time n, and that's it. We don't have anything at time n, and the right side will be u1 at time n minus 1. I'm sorry, u2 at time n minus 1. Okay, so if I put I equal 3, then I'm going to get minus alpha u2 at time n. So here's minus alpha times u2 at time n. And then the second term is going to be 1 plus alpha u3 at time n. So this is 1 plus alpha times u3 at time n. And on the right side, I'm going to get u3 at time n minus 1. So here's u3 at n minus 1. So you can see by just plugging I from 2 to m, you get a system like this, where you see that it is bidiagonal. So the main diagonal is minus alpha throughout, and then the super diagonal is 1 plus alpha. Everything else is 0. That's what we call it, bidiagonal. Now, how we impose the boundary conditions? We haven't done that yet. To impose the boundary conditions, we look at what we know from this unknown list. So from this unknown list, all I know is the concentration at x equals 0, because if you remember, that was one of our conditions in x. So remember, we had two conditions, one on x and one on time. The one on x is we know the concentration at every time at x equals 0. That is exactly u1 at time n. That means at any time point, including t equal to n. So we go back to here and claim that we know the first element, the first entry here. So because we know that value, we're going to multiply the corresponding column to this variable. The corresponding column is the first one, because first column is always get multiplied by the first element here. So I'm going to multiply this column by that value and then move it to the right side. That's what I have in red here. So this column gets passed over to the right side, multiplied by the value un, and we're going to change the sign of it because it's going from left to right. So on the right side now I have my original b vector with the addition of this known value at x equals 1 times the corresponding column of the coefficient matrix on the left. So now this system is well defined. I implemented boundary conditions. On top of it, the matrix now is a square. Before, actually, I had an extra column. So if you count the number of columns this way, you see that there's one more column than the number of rows. And by doing so, you're going to get a square matrix here. So we can now go ahead and solve this system. So for implicit method in time, exactly like implicit method in the space which we learned before, we need to solve a system. We cannot use like one line equation to solve for unknown exactly like in explicit methods. In explicit methods, we do not solve a system. So now we're going to look into the stability analysis of forward in space and backward in time, or explicit in space and implicit in time. So we're going to claim that this method is always stable, and any error that is created in there is not going to grow over time. So we look at this, the one-Neumann stability analysis. We plug in a generic form of c raised to the n power, which is the index of time, and then exponential of I imaginary number, k wave number, which is integer, times the x position at index j. Alright, so the j index is linked to the j index in u, and then the n is linked to the time index in u. Alright, so we're going to substitute all of our term ujn by c raised to the n power times the exponential of ikxj. That means we have to replace all these terms in here using the expression we have here. So that's the equation we have. We're going to plug in these terms in here. So the first term is going to be c raised to n power exponential of ikxj from here. This thing will be exponential of raised to the n power because that's the index in time, and then ikxj minus 1. This term is the same with the exponent of n minus 1, and then ikxj. We can cancel out e to the ikxj from both sides. This term get a factor of minus ik del x because it doesn't have ikxj. So if I multiply it by negative ikxj, then this exponential becomes ikxj minus 1 minus ikxj, and then xj minus 1 minus xj become del x. So from here we can now solve, we cancel out, by the way, we cancel out exponential c raised to the nth power. Also we can cancel out exponential of ikxj. So what we are left over with is the first term 1 plus alpha times c, second term minus alpha c times the exponential of minus ik del x is equal to, and then everything here will be cancelled, we get just 1. So from here we solve for c. The goal is to show that c, the magnitude of c is less than 1, and it doesn't change with any variable. So let's look at magnitude of c. c is by default imaginary number because we have an imaginary number down there. To get the magnitude of it, we have to multiply by its complex conjugate. So here's c, here's its complex conjugate, but I just shift or flip the sign of exponential or the imaginary number here. Alright, so if I multiply this by this, you get completely real value. Let's do that. So here I'm going to expand this thing. It's going to be cos del x, k del x, plus, because there's a minus sign already here, so it's going to be plus I alpha is coming from here, and then sine k del x. Here we can also expand this exponential, and it's going to be cos k del x. This time is minus I sine k del x. Alpha again is the factor up front. So we're going to multiply these two parentheses downstairs, and if you do that, then I have 1 plus alpha minus alpha cos del x in common between the two parentheses. So I get this term squared. And then I have a plus here and a minus here. So if you do this, you get a negative of this whole thing squared, where I squared is going to be negative 1. With the negative 1 you get plus, and then alpha squared sine k del x squared. So anyways, if you multiply these two, you get this. You're going to prove that this is always less than 1. So let's see why this is so. You can expand. The first term is going to be 1 plus alpha squared. And then the second term is going to be alpha cos squared. I have also alpha sin squared. So total is going to be alpha squared, because sin squared plus cos squared is 1. So I'm going to get 1 plus alpha squared from here, and then plus alpha squared from these two, minus 2 times the first times the second. So here's the cross product. This has to be less than 1, or we're going to prove that this is less than 1. So let's group the common powers of alpha. So I have alpha squared. If I factor that one out, you get 1 from here. You get another one from here, so it's going to be 2. That's the 2 factor up front. And then I'm going to have a cos k del x. So for alpha squared, I have 1 from these two, and then minus cos k del x from that term. Alright, so then what is the coefficient for alpha? I have a 2 here, which I factor already here, so you get 1 there, and then minus alpha times cos k del x. I get just minus cos del x, or I factored alpha out here. So that is the alpha term, and then the constant term is going to be just this, because I factored 1 out, I get 1/2 here. So let's call this A, B, and C, the coefficients for alpha. Because b squared minus 4ac is less than, if you do the math, plug in the numbers, you see that this is equal to minus sin squared and is always less than 0. Because this is less than 0, that means this thing, which is a quadratic function, alpha, has a minimum. To find its minimum, we get the derivative of down the stairs with respect to alpha. So that's what I did here. If you call this f and take derivative of it with respect to alpha, you get an equation like, this is f, which is down the stairs. You get derivative of it with respect to alpha, you get this, where you get alpha times 1 minus cos from the first term, and then plus 1 minus cos from the second term. You set that to 0, and you find alpha has to be minus 1/2, because these two cancel out. So that means the minimum of this parabola happens at alpha minus 1/2. But what was alpha? Well, alpha was v del t over del x. We know that this is always positive. So we cannot accept this alpha. Instead, we argue that the minimum of this parabola, the minimum of actually this parabola, or this parabola with respect to alpha, is happening at our alpha minimum, which is the minimum we can put is 0, because this is always bigger than 0. We cannot put a negative value here. So at alpha equals 0, what we get for this f function, we're going to get basically 2 just times c, because alpha is 0. What was c? So c was 1/2. So 2 times 1c is just 1. 1 divided by 1 is 1. So what we proved that is that downstairs is always bigger than 1, which means this thing is always less than 1. So we proved that the magnitude of c is always less than 1. That means this method is always stable. C doesn't change, doesn't grow in time, because it's always less than 1. And any number less than 1 raised to higher power always shrink. Alright. So we proved that implicit in time and explicit in space, or backward Euler in time and forward Euler in space, is always stable, or we call it unconditionally stable. Alright, so now in the next part of this video, I'm going to show you 2 examples where we also have some MATLAB script to basically execute and see how the solution comes about using forward Euler in time as well as backward Euler in time. So in the next video, I'm going to show you the MATLAB scripts. I hope this is useful, and stay tuned. Thanks for watching.